Welcome back to Math 103. This is video number 26 on growth and finance. Our task now is to find the value of this sum that is equal to the account value at the end of 1 year. The story was that you were saving $100 a month in an account that pays 6% annual interest, but it's compounded monthly, and that's why the monthly growth factor is 1.005. The amount of each regular payment is $100. The interest rate is 0.06 over 12, that's 0.005. When I say interest rate, I mean interest rate per compounding period, per payment period. That's what we need in this formula. Finally, the number of payments is 12. We are explicitly told that there is one payment per month, and this goes on for 12 payments. N always counts the number of payments. Substituting these values into the formula gives the following. The value of our sum, that is the future value of the account at the end of 12 months, equals payment times 1 plus the monthly interest rate raised to the number of months, the number of payments, minus 1, over the monthly interest rate. That equals $100 times 1.005 to the 12th power minus 1, all over 0.005. That equals $100 times 0.06167781 in the numerator, all divided by 0.005. Now, that might seem like more significant digits that you need to worry about in the numerator, but it's better to have too many than too few. You can always round off at the very end of the problem to the accuracy that you need. But if you start rounding too soon, you will lose significant information that you'll need later on and won't be able to get it back. So we have $100 times 12.3355624 once we carry out this division right here, and that works out to $1,233.56 in the account at the end of a full year. Notice that that is plausible. We've made 12 separate $100 deposits, and we're earning a little bit of interest along the way. We end up with a little more than $1,200 at the end of the year. Our more challenging task from last video is to find out how much money would be in the account at the end of 2.5 years if you deposited $100 at the end of each month, but the annual interest rate were only 5.4% compounded monthly. It's only more difficult in the sense that we have to think a little bit harder about the number of payments and about the monthly interest rate. First, it's a good idea to check that this really is a job for the future value annuity formula, that this really is an annuity. And it is, because you're making many deposits of $100 at regular intervals. It's not just one time that you're depositing $100, it's many times. Great, so this is an annuity, and we need to figure out what are the inputs to our formula. First, let's really understand what that initial deposit of $100 eventually grows into, and then we can understand what the many deposits of $100 each eventually grow into. That will help us understand what to plug into the formula. Each month that the money is in the bank multiplies by the monthly growth factor. That's 1 plus the yearly growth factor divided by 12. 1 plus 0.054 over 12. This turns out to equal 1.0045. So next we have to figure out what power to raise this to. In other words, how many times does the bank have the opportunity to multiply by this monthly growth factor? To figure this out, think of it this way. In the first year, there are 12 payments. In the second year, there are 12 more payments. That's 24 payments over the course of 2 years. And in the remaining half year, there are 6 more payments. So 24 plus 6 is 30 payments total. So this very first payment gets to sit in the bank for 29 complete months, from the end of January of the first year to the end of June, the third year. That's 29 months that this sits in the bank, and 30 payments total. Once we've done the hard work of figuring out what your first $100 deposit eventually grows into, and in doing that we've reasoned out how many payments there are, now the rest of the sum follows in the usual way. And we can say that the payment amount equals $100, the interest rate is 0.0045 as a decimal per compounding period, per payment period, and the number of payments is 30. We are ready now to use our formula to compute the value of our account after 2.5 years. The payment amount is $100, 1 plus I is 1.0045, n equals 30, I equals 0.0045. We compute, and at the end of the day, we find that the total account value equals $3,204.23. This makes sense. There are 30 separate payments of $100 each. They earn some interest, so at the end of 2.5 years, the total account value is something more than $3,000. Our next example illustrates an important point we'll need to understand about what fixed deferred annuities really are, as opposed to installment loans, which will be our next topic. In this example, someone you know borrows $250 at the end of each quarter from a lender with an APR of 20% compounded quarterly. So quarterly transactions and quarterly compoundings. Your friend keeps borrowing this amount every quarter without paying anything back yet. So eventually your friend will have to pay the loan back. But for the moment, there are newer and newer $250 borrowings, and there is debt that's accumulating. So we can ask, what is the total amount which your friend owes at the end of 1 year, that is, at the end of 4 quarters of borrowing and accumulating interest on the debt? Before you go on to the next video, write out a sum of 4 terms which represent the total amount of your friend's debt at the end of 1 year. You might be thrown off initially because here we're talking about borrowing, and previously we talked about saving. But mathematically, they really are the same thing, and they really are set up in the same way. Instead of putting $250 into an account that earns interest in a way that benefits you, you are instead putting $250 on your tab, so to speak, and over time it accumulates interest that's working against you. But still, interest is accumulating on these regular $250 payments. So mathematically, this sum works the same way as if you were saving money in a bank account.